are some open problems that we need to solve before we can really start using teams of autonomous vehicles to collectively accomplish objectives. So the first thing I want to note is that, well, this is mixed success. All right. Yeah, cool. Is that we're already we're in mixed autonomy land. So we're living in a world where we have a mixture of kind of semi-automated and human drivers that are driving around on the roadway. And one thing I liked to do when I was living in Palo Alto was to kind of sit around and count the Teslas. And on a good day, you could hit like 5% of the cars on the road would be Teslas. So we're kind of entering this new era in mixed autonomy where level 2 is widely available. So we have about 1 million of these cars sold a year that have a mixture of automated distance keeping. So they automatically keep the distance car in front of them. They have automated lane keeping. Every major seller of cars has some car that has these features available in them. And so, given that we have these technical capabilities available to us, I want to talk about a particular example of what is possible today with those capabilities on cars. In particular, I'm going to talk about our work going from simulation to field operation, deploying cruise controllers. So this is joint work done with a huge number of people that I'm going to make a point to thank, where we worked on creating cruise controllers that could both simultaneously optimize the fuel model of a car and also smooth the type of stop and go waves that you see in this GIF here on the right. So you'll have the car start and stop and start and stop. And what was done in this project is that we designed a controller using large-scale reinforcement learning. We put that controller onto 100 cars, and then we deployed it onto the highway. And this was part of the Circles project. So this is what Circles stands for, and it was a huge consortium from a huge number of universities, spearheaded by Daniel Work and Alexander Bayan. And here's kind of a screenshot of some of the things that we had some overhead cameras on top that were kind of tracking all the cars. And so our goal is going to be to use deep reinforcement learning and these kind of semi-automated cars. I'm going to say autonomous cars, but I'm always referring to level 2 cruise controllers with automated distance keeping to improve traffic flow and energy consumption. And once again.
Oh, sorry about
that. Okay. And so the way that we initially went about this, and this is going to tie into the kind of the second phase of the talk, is that what we thought we would do is we would scale up reinforcement learning in a large simulator. We'd set up a simulator, there'd be 1,000 cars in it, we'd have some kind of collective objective, so in this case, smoothing the stop and go waves. We would build some high fidelity digital model, we would throw it into our RL black box, it would spit out a controller, we would somehow wrap that in a safety layer to ensure that it was absolutely safe, and then we would put that on the highway. And I'm going to actually skip this. I'm just going to assume we all know what RL is. And so when we did that, what we found was that the resulting stop and go waves that we were seeing in our simulator did not at all match the kind of stop and go waves that we would see in the real world. So over here, this is an example trajectory from a data set that was collected on the highway. And I think it's extremely interesting to look at because if you look at kind of the velocity patterns of a single car on that highway, you can see that, it starts off at some speed, dips, goes back up, dips, goes back up, dips almost down to 0, goes right back up. And then 10 minutes later is basically operating in free flow. And this type of really rich, kind of wild looking wave behavior is not really something that we were seeing in our simulator at all. The waves are much more regular. And I'm going to talk more about that at the end of this talk. And so instead of being able to use a simulator like we wanted, we instead had to collect a lot of field operational data. I mean, a lot, not actually that much. So what some poor undergrad would do is they would go on the highway during congestion, and they would drive around with a radar-enabled car, and they would collect the trajectory of the car in front of them, and with a GPS kind of tracker on the car, they would also collect the trajectory of the car themselves. So they would get on the highway during congestion, do this extremely boring drive, back and forth between these two locations. And then we would record that data and use it to form a data set. And then instead of a high fidelity digital simulator, all we would do is we would play those trajectories back. So we would take one of the cars and we would just kind of replay its trajectory as the front of a platoon. And behind that platoon, we would place a bunch of human-driven cars. So those are the white cars. And then in red, we would have an AV every like 5 or 10 cars. And right now, they're not doing any traffic smoothing. They're just kind of doing what a human would do. But you can see kind of these stop and go waves propagating back caused by the fluctuations in the car at the front, this blue car. So an important question, and something that we're going to talk about more throughout this talk, is what are we doing for those human drivers, so those cars in white? And what we would do is we would have them drive according to a parameterized car following model. So basically, the car would respond to its own speed, the speed of the car in front of it, and the distance to the car in front of it. And here's kind of an equation for that. And in particular, the driving model that we used was the intelligent driver model, which is a very common driver model used in microsimulators. And an important aspect of this intelligent driver model is that it is wave propagating. So it will create kind of these stop and go waves that you observe instead of dampening them out on their own. And when we do that, and we take this plot here, time is on the x-axis and position on the y-axis, and each line in here is an individual car trajectory. So when we replay kind of the trajectory of one of the cars from the highway, we can see the kind of stop and go waves as these kind of downward sloping black waves. And so as the human drivers encounter the fluctuations of the car in front, they kind of propagate the waves backwards. So we set up our simulator. We have this kind of single string of human drivers and AVs mixed together, following behind a replay trajectory. We kind of threw it into the RL black box. And in trying to be the good kind of machine learning person, we kind of benchmarked our RL controllers that we would get by trying to optimize the energy consumption of that system against a bunch of model-based controllers that we spent a while designing, a very large team. We confirmed that RL controllers kind of were doing the best in terms of fuel economy while not decreasing the throughput or the speed too much of the highway. So we have our RL controllers. We swept them out over some held out data set to ensure that they were actually kind of generalizing in the way we would like them to. And then we were ready to put them on the highway. Really quickly, you can kind of see what those RL controllers are doing. So over here on the left, we have that kind of pattern I was showing you before, where we have 200 cars in a line, and we see the stop and go waves as the downward sloping black lines. And basically what the RL cars are doing is they're kind of dynamically opening up these thin white lines, which are gaps that when the wave runs into, it kind of smears out the wave across thing. And because the energy models heavily penalize accelerations, kind of smearing out the waves and decreasing the fluctuations have really sharp improvements in fuel consumption. Okay, so we then proceeded to do a large-scale deployment. So these are 100 Nissan Rogues sitting in a parking lot, each equipped with a Raspberry Pi and some amount of a Panda that would allow us to actually do control over these cars and sensing. And then over 5 days, they would just run back and forth on the I-24 in the hopes of encountering a wave and smoothing it out. The controller design for this actual experiment was spearheaded by Kathy Zhang and Nathan Lischle. So I just wanted to shout them out. And so, yeah, we would then deploy those cars over the highway. Sensing was provided by the I-24 Motion Project, which are these 300 cameras that are sitting overhead on this highway. So this I-24 corridor over here is one of the most instrumented corridors in the world, and it's generating immense amounts of data of human driving. So really recommend taking a look at it if you want a gigantic data set of human driving. And so we could follow along the trajectories of any of the cars. We could detect stop and go waves. We could measure the miles per gallon of the cars both locally and through their camera trajectories. So we ran our cars over 5 days. Some of those days were congested, some days were uncongested. And then at the end, we compiled all of that data and tried to figure out ways to assess whether the experiment was actually successful and whether deploying these 100 AVs onto the highway improved the fuel consumption of the highway. And unfortunately, it's kind of tricky to say whether the experiment is a success due to the challenges of counterfactuals, right? So it's hard to say what would the congestion have been that day had we not deployed things. So we have this kind of qualitative measure that we're using right now. as an approximate metric of success. And the idea is that we're going to bin all the cars by their distance to the AV in front of them. So we're binning them into 50-meter bins. So is there an AV 50 meters in front of you, 100 meters, 150 meters? And the idea is that as you get further away from the AV, its impact is presumably lessened. So as you get very far away from any nearby AV, you're basically in fully human-controlled traffic. And these closer bins, you're in somewhat AV-influenced traffic. And what you can see is that as you, so over here on the y-axis, we have the average fuel consumption in gallons per second. You can see that when you're close to an AV, that fuel consumption is low. As you move away from that AV, that fuel consumption goes up. Similarly, the standard deviation of that fuel consumption increases as you move. So it seems like there's more fluctuations further away from the AVs. So it kind of looks seemingly like the right thing is happening. And there's a lot of work that's still being done to kind of more precisely assess this impact, but it qualitatively looks like a success. Okay, so this is kind of a case study, hopefully showing some of the things that can be done right now with the type of penetration that we have, and with humans in the loop, carefully design abstractions and simulators to do this to design the controllers. And so what I want to do in the kind of the latter half of this talk is to talk about where we'd like to be, having looked at some of the things that happened and some lessons from there. So what we really wanted at the beginning of this was to have kind of a scalable workflow. We wanted to have a calibrated simulator. We wanted to throw that into our RL black box and have controllers come out of it. Right? So calibrated simulator goes into black box optimization, spits out some fully decentralized controller. We put that on the highway, hurrah. And I think a lot of folks think that like this whole loop right here, this black box optimization algorithm or some optimization algorithm, and the controller designer is the hard part. And after about 3 years of this, I am fully convinced that, in fact, this is the hard part, that designing calibrated simulators is the place where we really struggle and is where we spent, honestly, most of the time in this project. And I think there's kind of a really big simulator gap between what the micro simulators generate and what you actually see on the highway. So over here on the left, we have a bunch of like observed waves over 2 different days on this I-24 motion thing, and you can see that they're highly variable. On Wednesday, we have these kind of little waves and mostly free flow. On Monday, we have extreme congestion that is persisting for a long period of time. And when we looked at the waves in our micro simulator, they looked like this, and they always looked like this. They were these very thin waves occurring constantly at all times, no matter what we did. And they're always thin. So if you look at kind of real waves, there's a lot of variation in their spacing and their thickness. And just no amount of work that we tried to do on the simulator side was able to reproduce that. So there's something really missing. And basically, the way that we were able to make it work in this project is we had a human-guided abstraction. We said, really, mostly what you care about is a single lane. We're going to neglect interactions between lanes. And we're going to collect some amount of real-world data and assert that that is our calibration procedure. So we were able to resolve the fact that we didn't have a good microsimulator by collecting data and having a human in the loop, doing this kind of domain knowledge and converting it into the appropriate abstraction. And that's really, I think, not where we want to be. And I think the main source of this, or my belief, is that the problem here is human models. So the human models that we have inside of microsimulators, and in fact, in a lot of simulators, it's not just Sumo and AIMSUN, it's also Carla and NewPlan, are like really not fit to tons of data. So we don't have great merging models. We don't have great lane changing models. The car following models have tons of free parameters that you can pick, and the ones that you pick affect the waves that you see in them. And just to note, I mean, there'll always be some parameters that require calibration, but I think we're really lacking on the human model side. And one of the ways that people are trying to fix this is through kind of incorporating a lot more ML. So moving away from these small parameterized car following models to kind of big data sets of driving that we then convert into models of human driving. So we take some big collected data set of human driving. So here's a bunch of scenes. We throw that into an imitation learning algorithm or some kind of supervised learning algorithm, and we get a human driver model out. And I think this is a great idea, but just from the micro simulator side of things, I want to throw out some problems that I'm seeing in this land. So our criteria is that we have a simulator with thousands of cars where the rollouts go on for minutes or hours. And so what we need in microsimulator land is models that basically never crash and can be run really fast. Because when you have thousands of them, your simulator time blows up when you start throwing neural nets into everything. And it's not clear that the supervised learning models are actually learning the things that we want them to learn from the microsimulation perspective. So I'm actually going to skip this slide and instead talk about this slide. So this is a kind of a set of kind of ML models that were benchmarked as part of like the Waymo Open Sim Agents Challenge. And these are a bunch of different metrics for how they were scored in that challenge. And the thing that I really want to draw attention to is that when you roll out these ML models for like 10 seconds or so, they start to acquire really high collision rates and really high off-road rates. So kind of the best one that they benchmarked in the Waymo Open Sim Agents Challenge, and this is true for other models like UniAD and other things, is that when you roll them out for 10 seconds, they collide 1 in 10 rollouts, 1 in 30 rollouts. I mean, these numbers are going down over time as we get better at training these models, but they're kind of in the place where if you inserted them into a simulator with 1,000 cars, eventually it would just be cars crashed on the road everywhere. And so you can't actually run the micro simulation that you'd like to run. So yeah, these models crash if you roll them out too long. They're not exactly where we want them to be. So kind of comparing the kind of advantages and disadvantages of these two things, we have these car following models. They're pretty inaccurate. They don't model human driving behavior super well, but they do have physics and causality baked in, and they're fast. You can explicitly make them not crash, and they're inherently factorized. So they're on the car. They're not like one big centralized model that decides where every car goes. On the other hand, we have supervised models that are accurate, and they scale with data, and that's amazing. But they are kind of slow to do inference on, and it seems to be sort of hard to get all the crashes out of them. And I mean, this will probably get better and better over time. I'm just kind of, this is the state of the world as I see it right now. So I just want to end by kind of talking about, of course, what our current hope is in terms of how we get these better human driver models. And because I'm a man of one hammer, I'm going to say that it's going to be reinforcement learning. So kind of the way that I see where we live in the world of building human driver models is we have a little bit of data. When I say a little bit of data, I can mean like, millions and millions of driven miles, but much less than the amount of data we have of like all internet text data or all internet video data. So we have a little bit of this data collected offline over some trials. And so we wind up in this like kind of living somewhere on the spectrum between having no data, where you want to kind of design all your models by hand, you want to design your cost functions by hand and optimize through them, and kind of infinite data, where you probably just want to do something supervised. And we're kind of in this middle space where I think the thing we could try to do is to kind of mix this data, but with like large-scale game theory priors about how the agents are going to interact. So combining data with like large-scale, like multi-agent equilibrium finding. So let's see how far this gets us. So I'm going to like briefly talk about some work my PhD student Daphne Cornelius has done on human compatible driving partners by combining data and large-scale self-play RL. And the way we do this is we have the simulator that we've built called Nocturne. There's a new version of it coming out that's GPU accelerated sometime next week. And the idea of Nocturne is you're going to like replay collected driving patterns from either the Waymo Open Motion dataset or the New Scenes dataset. The agents have restricted fields of view, so you can kind of see what the agent sees on the right. And we're just going to do large-scale self-play reinforcement learning. So each agent knows its goal. It doesn't know the goals of other agents. And they can also rotate their head, which is just a cute thing we have in the simulator, because I want to see them do implicit communication. So we run RL at scale. We can get agents that get to their goal 100% of the time without ever colliding with another agent. And these agents, unfortunately, look kind of like this. So this is how they get to their goals. And if this is bad, it only gets worse. So this is what you get if you just like run self-play without any data priors. And so what we did in this paper is we just did kind of the simplest thing you could possibly do is kind of to take the RL objective and add an objective of staying kind of close to an imitation learned model. We don't do any reward shaping because that would kind of defeat the purpose. So our agents just want to get to their goal and stay close to this human behavior. So kind of this term right here is both doing equilibrium selection in the multi-agent game, and it's also kind of doing some rewards about how humans prefer to drive. So what we do is we pre-train a 50% goal rate reaching model as a regularizer. This is a super bad imitation learning model. You could definitely do a way better job than this. And this terrible imitation learning model is partially why is a real limiter in our results. But we trained this model over 200 scenes. We evaluated over 10,000 scenes. So these are kind of some of the scenes we do in there: parking lots, highways, that kind of thing. Yeah, so just a kind of quick overview of the results before we get to questions. So we want our agents to be both human-like and good at getting to their goals. So is that what we actually get out of this? So a couple measures that we do is kind of what we call goal-conditioned average distance error, which is how close did you get to your goal, but measuring the trajectory distance between yourself and the human at each step. And then action differences, which is how different were the actions that you took, because you can kind of follow the same trajectory, but you can follow it jerkily or less jerkily. And what we see is that here on the x-axis, we have this goal-conditioned ADE, and on the y-axis, we have the goal rate, which is how often you get to your goal. The pure imitation learning model is very accurate at mimicking the trajectory, but almost never gets to its goal. And as we throw in more and more RL, we can kind of increase the goal rate while slightly increasing the kind of trajectory distance. And these are results from 6 months ago, so all these numbers are much higher now. And kind of a similar thing is observed with respect to the action differences. So how close are the steering actions to the actual actions that were taken. Our agents are also closed loop effective. So when played against each other, they get to their goal 95% of the time. And in log replay, which is kind of a proxy for interacting with humans, where we kind of just replay trajectories that humans took. So you can kind of see this human on rails driving along. The inclusion of these data priors improve the ability to get to their goal by 15% relative to pure self-play. And this number kind of understates things because most scenes in the data set are just kind of straight driving. So if you actually look at what the improvement is of adding these data priors to really interactive scenes, where interactive scenes are measured by kind of how many cars trajectories you have to drive through, there's actually like a 40% improvement in the collision rate over there. So just to kind of look at what this looks like after we do this, and do these kind of mix of data and RL, there are just a couple failures remaining. These are like data set failures. So the Waymo motion data set has some goals that are unreachable because you can't cross these green lines. There are some training failures where we just like run into a wall every now and then. But then it's mostly those two things. 1/3 of the remaining failures are just these kind of coordination failures where we expect a car to move, but it doesn't. But kind of qualitatively, you see that the inclusion of these data priors into the RL loop kind of really change how it drives. So on the left, we have the video I showed you before, and on the right, we have what it looks like once you add this kind of imitation regularizer. Super boring. Does, kind of exactly what you'd want it to do. Yeah, so so some quick takeaways. So we can do traffic smoothing at current penetration rates, but we need humans in the loop to kind of do the model building and extractions because our simulators are not good enough. Improving our simulators is extremely critical, and we think like large-scale multi-agent learning combined with data priors can really help here. So huge number of collaborators on this. So I just want to thank them all here, and a large number of supporters. And then I also quickly want to shout out the folks in my lab. The Emerge lab. We're growing. We forgot what our acronym is. So right now we're just going with Eugene, Machine Eugene, Reinforced GPU Eugene. So if anybody has a better acronym, we really appreciate it because we've forgotten what it is. And yeah, thank you. Questions? Cameron?
You mentioned that a lot of attempts were made when you were showing the different, like the simulation kind of thing, like
Yeah.
congestion curve.
Hmm.
You mentioned just you tried a lot of things and nothing you could do to get it to work. What were the things, like, were you just tuning IEM parameters or were you?
Yeah, tuning IDM parameters, tuning lane changing model parameters, tuning the boundary conditions. Like there was an on-ramp there, and we tried to tune like the kind of priority that the on-ramp was given, stuff like that.
Did you change the effective in the simulation, like the effective speed limit? I mean, did you change anything that would not be IBM parameters, but would
We played with the speed limits too. Yeah. Good question.
Just quick questions. So you mentioned the desire to reduce fuel usage and smooth traffic.
Yeah.
Are those objectives ever intentional with each other, or by just aiming at fuel use, you automatically get smooth traffic as well?
So if you try to improve MPG, I think you can really improve MPG by driving at like exactly what the optimal energy consumption of the engine is, which for some of these cars like 11 meters per second, which is slower than the speed you want to drive. So they are intentional a little bit. I don't have this graph here, but the improving the stop and go waves though is just kind of free low hanging fruit. When a car does this traffic smoothing, its energy consumption improves, the energy consumption of the cars around it improve, and there's no real loss of throughput. So kind of in the operating regime that we are in, these things are not really intention, but if you just want to optimize miles per gallon, then you do wind up throwing away a lot of throughput.
And then kind of more speculative question, since prompted by the observations about the crash rates of the driver models, like what fraction, how much gain do you think potentially could be made in fuel use by eliminating crashes and the resulting backup?
Oh, yeah. I mean, I think a huge number of these stop and go waves are generated by congestion on the highway caused by like a lane closure caused by a crash. I think that overall these stop and go waves are like, I think you spend like, I don't know, like 2-3% of your total driving time in them, something kind of in that order of magnitude. So I assume that I don't know what fraction of that is caused by collisions on the roadway, but that's kind of the regime that you'd be in. Other questions?
All right, so I have one. I was wondering if you could connect the dots a bit between the first part of your talk and the second part of your talk.
Yeah.
So in particular, could you comment on the current benchmarks available for reproducing or basically making progress on data-driven simulation at the traffic scale, whether these benchmarks exist? What do we need to get there? What kind of metrics? Just sort of your take.
Yeah, that's a great question. So there are a lot of benchmarks at kind of the smaller scale, like, like 10 to 100 cars operating like kind of at an intersection or maybe an extended thing, kind of like 10 seconds of extended things. There's a lot of research and benchmarks for that specifically. I think for for actual traffic modeling, I'm less aware of benchmarks studying that. I assume that there's kind of a connection between the two, and that if you're precisely getting like the micro mobility correct, then if you were to scale that up, I assume you'd reproduce macro phenomena. But I think it's not clear if that's true yet, right? Like we don't really take these micro models and then test whether they reproduce macro phenomena too often.
Or I guess I was wondering, like, is there some benchmark that you could like apply the second part of your talk to the first part of your talk?
Yeah.
Like how different with the simulated waves?
I see. So this is ongoing work. This is something we'd really like to do is as once we get the crash numbers a little higher than they are, right? We have 0 crashes in the fully RL regime, but many more crashes in the combined RL imitation learning regime. So it's not, once we get that crash number down, we really want to take those cars, stick them inside of Sumo, and see if we reproduce the macroscopic phenomena, but we haven't had a chance to do that yet. That is kind of connecting the dots, as that's where we'd like to go, but haven't gotten to yet.
I have one small one actually. Do you also think about what kind of safety guarantees can you provide at the end with the mutation plus RL algorithm?
Yeah, so I think generally the best thing that we can provide is like statistical guarantees, right? Like we ran this for 100 million hours and observed 0 collisions inside those 100 million hours of driving. You obviously could, we would like to and are trying to provide like adversarial robustness guarantees. So if one of the cars is an adversary, can we minimize the regret and guarantee that there are no collisions that we could have avoided? In terms of like explicitly guaranteeing that they never collide, we could wrap them with things like control barrier functions or things like that. But then you get into a regime where those control barrier functions occasionally cause you to not be able to drive forwards. So right now we're mostly focused on statistical guarantees, just like we ran it for 100 million miles, no crashes in sim.
Do you think like the control barrier functions would really go against what the algorithm is trying to do and kind of stop it or bring down the efficiency?
I think that, well, no, they're pretty, I think they're reasonably cheap to run from the efficiency perspective. It's just that as you get to the like 0 collision place, you start to run into like the edges of the control barrier functions having some additional problems. Where they provide safety, but also induce additional challenges.
So you talk a lot about like trying to get to zero crashes, but it seems like you would want some amount of crashes if you want the more faithful representation of the like spikes in traffic.
Yep.
These crashes. So do you feel like the goal is really 0 or something more realistic? And also the current state of simulation, if there is a crash in it, is there like a notion of pile up and increased waiting times? Or is it just there's an overlap in the footprint of the vehicles?
Yeah, that's a great question. So congestion here can come from 2 sources. So there's the congestion caused by a car being in collision and that causing a pileup. It can also come from just like these like spontaneous congestion caused by like a lane change or something like that. And so we can address that in this framework without in kind of the 0 collision land. With respect to actually getting the human driver model to collide in a calibrated way where it collides at the appropriate rate that humans collide and in the way that humans collide, I don't think I have a great answer to that yet because we don't have all that much data about, human collisions. And so it's not clear exactly how you'd confirm that your human driver model that collides in the way that you would like it to collide, right?
Oh, I mean more like that's great.
Yeah, so I think that, we could eventually get to the place where we are colliding at the rate that humans do collide, but I wouldn't be confident that we were colliding for the same reasons that humans collide. I guess getting to the rate would still let you reproduce probably the macroscopic phenomena, but, I wouldn't be confident about it. Yeah, there is. I mean, depending on the simulator, a lot of them just teleport the car away, but you can leave it there.
Just one last question, maybe another question really. Have you said about the macroscopic phenomena where the car actually drives the whole way from using all the kinds of special things that we are running on it? Have you tried using it, at least some of it, that there's a whole end-to-end, it takes the turns, it tries to change lanes, and all of it in one single simulation?
Do you mean have we tried to like run our human driver models for like an extended period of time? Not really, not yet. The snippets that we train them on in the simulators are only 10 seconds long, so the map runs out. Yeah, that's the problem right now. All right, thank you all very much.